What letter is this?
X.
This is the x component. Okay, your x. They didn't write that. That's what's meant. This is what?
Y.
So again, here we go. Let's make our table. We can call it my table. It wasn't given to me, but I'm going to make it. T, x, and y. How far are we going?
0 to 2.
This can really help you when you get stuck, because you're like, what are the endpoints? I don't know. You got to go from t equals 0 to t equals 1. Well, what's the x and y at t equals 0? X is, see what you're doing? It's the idea of parametric and Cartesian, and we're connecting them, all right. And what's this value?
0.
So at t equals 0, x is 1, y is 0, right? What's going on at t equals 1? 2 and 1, yeah. Let's plug it in. Well, where's the values? And I got to plug in f of, that's the endpoint, right? Minus f of, right? Let's go find them. What's f of 2 comma 1? Look, that's an x, that's a y. That's an x, that's a y. Let's read this table. We'll circle. We'll circle. What's going on when x is 2 and y is 1? 25?
Mm-hmm.
That's the number. And what's going on when x is 1, bless you, and y is 0? The number is what? There you go. What's the line integral? 20. No, but think, does that take long on a test? Not at all. But it definitely could leave someone stumped if they're like, where's the vector field? Where's the vector field? I don't see anything. It can really confuse you. They're saying, hey, this was already given to you. But then there's the mystery. The idea of parametric Cartesian. Now you're going to love this. Green's theorem. Green's theorem is for closed paths. Let me say that again. And it's only for two-dimensional vector fields. But this is the coolest theorem. Green's theorem now when this is in section 16.4. Boy, you're going to like this. Is for closed paths. Only closed paths. Green's theorem is only for closed paths. Okay. So what's a closed path? Can we draw some pictures of these? I'm talking about a path that started at one point and it ended at the same point. So hey, here's a closed path. Go over here, cut up here, go back here, and go back like that. Maybe a square, right? Or a rectangle? Isn't that a closed path? Now can you imagine doing that line integral directly? How many line integrals would it take? 4 of them. You would need to do one for that path, one for that path, one for that path, one for that path. You follow me? What's another closed path? How about a full circle? Like that. That's a closed path. What's another one? A triangle? You went up here, you cut over here, and you came back there. I just want to give you some examples. Here's another one. You went over here, then you swung along a semicircle and came back here. These are all closed paths. Green's theorem is for these types of problems in vector fields. He's got an awesome, awesome theorem that says to do the vector field, the evaluation of the vector field, if the P and the Q are the P and Q components of the vector field, so when I write this, if you got let's just call this P and Q, he's saying that the line integral will always equal a double integral. D is the region that bounds that closed path, like the region inside, think area. For a double integral, and he just does dq dx minus dp dy. And I gotta squeeze in way at the end, everyone, you know when you write like your dy dx or your dx dy, I'm gonna put a dA here. Right there. Yeah, just for dx, because you might choose to do dx dy or dy dx. Can you go polar? Yes, if it's circular or semicircle, you're going to want to go polar. Sound cool? So I will make a note of that. Don't forget about that. Go polar on this baby. And go polar on this. But this is super duper. Now you might say, oh, I'm going to forget this theorem. Okay, but I don't know if you'll finish the next test, because how many line integrals would you have to do for that problem directly? 3 of them. You'd have to do, if I made you go along this path, you'd have to, let's say you started here. You'd have to do a line integral for that line, then add that answer to that line integral, and then add that answer to that one, right? It would take what? Very long. Was this be super fast? Or if you did this one, the rectangle. One for that, one for that, one for that, one for that. We're just saying this is the D. Now I do want to point out, this theorem is defined for, make sure you have this in your notes, for when it's counterclockwise. That means positively oriented. So this is the theorem if the path right here is positively oriented. What do I mean by that? It moves in a counterclockwise direction. Which way is that? Counterclockwise is going like this. So that's positively oriented. But what would positively oriented be in a rectangle? Like this. Like that. So my question is, what if the path is the other way? Yeah, you could do the math, all the math, and then change the sign, or you can invent a whole new theorem and just do this minus this. Does that make sense? Mm-hmm. So let me say it again. If you're going clockwise, and you want to use Green's theorem on a closed path, you can either just do all the math and put a negative for the final answer. That would be one way to do it, right? Or you could say it's the double integral of what? dp dy minus dq dx. Cool. Whatever you find easier. That's if it's what? If it's going clockwise. Cool. Hey, and we'll work up. This is fun. So all we got to do is now just a double integral. We don't have to spend all that time doing the line integral directly, right? We'll do a couple of these. Hey, there's something else I wanted to wait till now to tell you about the fundamental theorem of line integrals. Fundamental theorem of line integrals dealt with what kind of vector fields?
Conservative.
Guess what the line integral comes out to be along a vector field that's conservative? If you do a closed path, it will always come out to be 0. So would you put that in your notes right now? And we can see it right now. If the vector field is, I wanted to wait till now so you can stumble upon it. If the vector field is conservative, what would be the line integral along a closed path? The line integral would always come out to be 0. And can you see it right now? Look what would happen. Remember what we said about conservative vector fields? These two would be what? Equal to each other. Do you see that? That would mean these are equal. And what do you get? This minus this would turn out to be what?
0.
So I wanted to wait till now because that connects to Green's theorem. That if you take a if you're in a conservative vector field and you take the closed path, the line integral always comes out to be 0. Cool. And everyone has this practice document, right? Could you just tell me which one of these it's going to be 0 on? Let's see. I'll fire that up. Oh, this only takes a second. We just got to look at the 3 vector fields. I just want to see there's 3 vector fields there. And we're going to see which one is. Ooh. Zoom. Zoom, here it is, number 9. Thanks for your patience. In each vector field below is the vector field conservative. And I got these vector fields, but you notice I drew a blue circle? Because just as an example of a closed, did you have to take this closed path? No, but I just thought it'd be an easy thing to do a circle. And what I need to do is explore and just think about if you took this path right here, would you get a line integral that's equal to 0? How do we do this? We're looking at the vectors. Do all the vectors seem to be perpendicular at every point of tangent? So that'd be like doing a sum dot product to 0, right? So do you all agree? Does it look like the line integral would be 0? Like aren't those all perpendicular there? Can you see? That all those vectors along this path would be perpendicular. And what's the dot product of two perpendicular vectors?
0.
0. So this one looks like that vector field's conservative. And it is. How about this one though? Let's just start right here. Looks like this is going in the same direction. Now these are going what?
Opposite.
Against it. These are going with it. Now these are going against it. What do you think? What's your hunch? Does that look conservative? Remember, all we'd have to do is have the vectors like almost like in terms of symmetry. Half are going against and half are going with. Does this look conservative?
Yeah.
You are correct. This one's conservative and this one is conservative. Can you tell? It's like these are going with it a little bit and then these are going against it. And from here to here, going with. Now these are going against. How about that last one though? I think it's quite obvious. And go along this path, what's happening? All the vectors are what? Going against the grain, so is this vector field conservative? No. So we just look, isn't that cool? This is one way you can look at a vector field to see whether or not it's conservative or not. You take a closed path, and you see if the vectors would come out in terms of the line angle would come out to be 0. So I just wanted to say that to you. Hey, cool. Okay, so we'll work through problems, we'll be done. Of course, you know I'm going to give you a couple closed paths. That shouldn't be too bad. Let's see, here's my first one. Let's use this theorem. When do I use this theorem? For closed paths. So here's the first one. Can you compute the work done by a vector field? This is from the problems if anybody wants to read it off their sheet. Number 10. And you got to do, everyone, here's the vector field. Five y, 6x plus y. Now notice they wrote on this problem that this was the path. 5y here, dx plus 6x plus y, and dy. They want you to evaluate this, that's a 6. They want you to evaluate that line integral, and they said C is the closed boundary of a triangle. And you go from, it's oriented counterclockwise. And you got to go from the points 0, 0 to 4, 0 to 0, 2 and back to 0, 0. Oh, evaluate this directly. That would take a while, wouldn't it? Let's use green theorem. What does that look like? 0, 0 to 4, 0. Where's 0, 2? Right there? And then back to here. Counterclockwise. That's D. Want to go green? Go green! Alright, what's d q dx? That's q, that's p. Look, when they write in this case, that's your p. That's your q. That's your p, that's your q. What's your q with respect to x? 6. What's your p with respect to y? 5. You want to do dy dx? I'll keep it dA from now. What's the double integral of what? Well, 1. Now, if I do dy dx, who can help me out? How would I do this? 0 to 4, how to find the equation of that line? mx plus b, what's the slope? Negative 1 over 2x plus 2? Cool, I like it, I like it, I like it. And go from 0 to that, true? Everyone, there's got to be an easier way to do this problem. What does double integral find? Oh, excuse me, double integral of 1. Triple integral of 1 finds volume. What does double integral of 1 find? Area. Double integral of 1 finds area. So if you don't want to do all this math, can I just get the area of that rectangle? So I'm going to point that out. This should be equal to the area of that little triangle there. I just didn't feel like doing that math right there. Because double integral of 1 should find area. What's the area of that region D? What's half base height? Half base times height. What do you get? Is this 4? You know, I told you, I just want to save some time. Now, yes, you could have done that integral and worked it all out. But I like, when you get double integral, by the way, what if this came out to be a 5? You can factor out the 5 with this. Cool. And I thought for the last problem, the practice set problems, I've got a rectangle, same stuff, right? And I thought we could end, I got one with the triangle right there. Circle, you could go polar, right? So I thought I'd end with one that's kind of like a circle, but like a semicircle. Sound good? So here it is. I need to evaluate, I'll give you the vector field. Last problem, but I want you to go along this path here. I want you to start at the point -2, 0. All right?